Most of you have done, right? Yeah, two haven't. Okay, there are still few more, not yet. Okay, never mind. We will end the quiz at 11:30. So 6 minutes more. Okay, so, okay, 6 minutes more. There are some of you not yet done, so I will wait until 11:30. Okay, 11:30 the quiz will be closed. 11:30 the quiz will be closed at 11:30. Okay, so majority of you have done. Isaac, Shaline is not here today, is it? Shavaria. Oh, so many didn't answer the quiz.
I'm sitting.
In progress, in progress. In progress. Okay, in progress. Okay, okay. I will wait now. Some of you are in progress. Okay. Okay, 3 minutes left now. 3 minutes left. And then for those who finish, I just uploaded the lecture note, lecture 4, in the e-learning platform. You will see it. I just uploaded the e-learning platform lecture notes, number 4. Okay. Later I will create an assignment. Assignment is your group assignment, the mini project. No, still I have not created yet, so I have to create this and then you can submit. So for those who finished the quiz, please check the lecture 4, lecture note 4. The lecture note 4. Okay, 2 minutes left. Guys, 2 minutes left. The quiz will close in 2 minutes. Aha. Okay, time's up, I guess, but some of you not yet submit. Oh, I just, okay. So can we start the class now? Okay, so we'll start the class now, okay? Yeah, they are still one. Okay, so everyone done, okay? So I should have 36 students, but anyway, I only have 35. Okay, the quiz has done. Thank you very much for your cooperation. You guys have done a good job. Yes, Sean, anything? You guys
Oh, nothing.
okay. So thank you very much for your cooperation. I actually it is my first time to create a quiz in e-learning platform because be frank to you, just be truth to you that in this coming semester, actually start from last semester, we have to use this platform to do all types of learning and assessment. And I was not aware that we have to use the quiz, or else usually I like to play Kahoot and this kind of interaction game with the students now when we are in the class. But unfortunately, they set this type of stupid rule. Oh, okay. So anyway, that we have to use this platform, China. So we have to use this platform to do the teaching and learning. I find it is kind of not easy. It takes me some time to create the quiz. Well, anyway, it is not really user friendly. I also pity my students. Sometimes it's also very difficult for them to submit their assignment, their assessment, or all these kind of things. But anyway, at last we did it. Yeah, correct, right? Not only, actually also the student. I think we ourselves is totally fine. But the students, because we every lecturer we have only one or two subjects to teach, right? So maybe we create one or two quizzes and an assignment. But for you guys, like every subject, you imagine every semester you study 7 to 6, like 6 subjects now. And then all the subjects you have to enroll to this e-learning platform. And luckily, there are several students tell me that when I enroll you guys, somehow I enroll you manually because this has to be done manually. So yeah, but they don't want us to use the G Classroom, Sean. If you use the G Google Meet, that would be very, very easy to everyone. So it's no longer allowed to use the G Classroom. So only the G Classroom can be used during the teaching like this, the online teaching. So I was a little bit of like, anyway, I pity you guys. For myself, I only have one subject. Example, okay, one or two subjects, no? So create the assignment and quiz. But for you guys, you have many subjects, right? And then you have to be very careful when you enroll especially enrollment for the quiz, assignment, and sometimes the students, they have a difficulty in uploading their assignment in this e-learning platform and blah, blah, blah. So please let me know, okay? If you find you have a difficulty, please immediately let me know. Because example, like Esther, I can't remember, or who, she texted me, she said, Doctor, I haven't enrolled to the e-learning. Oh my God, because I do this manual key in, right? I may miss someone's name. No, although Sean gave me the full list, I have a 36 students. So, but however, and then some of them I tercicate. Example, I think it's Esther or any, and also just now, luckily she told me like Haswani. So please, if you are not in the were not in the e-learning platform, you have to tell me very soon because all the material I will put it in the e-learning. So Esther told me earlier, so I quickly enroll her. And only today Haswani baru beritahu saya apalah produk ni. It seems like you don't care. Hello, can you speak a little bit? Siapa? Haswani.
Yes,
You
Doctor.
Macam mana ni? Baru hari ni baru beritahu saya.
Yeah.
Then you don't care. I give you the lecture notes in the e-learning platform, you don't care. Ke you dapat dengan kawan lain, oh tak apalah, I get it from my other friends.
I got from my friends.
Okay, fine. Anyway, all things sorted out. I was like so panicked that when she told me, Doctor, I cannot answer the quiz. Huh? How come she cannot answer the quiz? What is the reason she cannot answer the quiz? Baru saya tahu dia kata dia tak ada dalam e-learning. Apalah budak ni. Okay. Well, okay, without wasting time now, let's start with our class. And then I will see you on Tuesday. And then you have a test on Wednesday. Right, I'll see you on Tuesday. Tuesday got another quiz. Okay, Tuesday got another quiz, but it's a simple one, not a difficult one. Okay, Tuesday we'll have another quiz, but that quiz is a written quiz, so you just need to prepare paper, no, and then answer the quiz online. Not answer the quiz in the class, no. So Tuesday will be another quiz, but a simple one. It's a written quiz. Okay. So bring the paper. Right, so let us learn together the lecture 4. Okay. I need to. Okay, everyone got the notes, right? I just upload it in our e-learning platform. Today I feel fresh after I back from abroad. Usually then I feel much happier when I come back and I see you. I'm very happy actually now. Okay, although it's in the weekend, I'm my sincere apologize that I have all the good kids like you. You are able to have the class with me because you want to have a long holiday, right, during the Deepavali. So you sacrifice this weekend, then you can enjoy Deepavali holiday. Correct or not? Is this your intention? Give me some reaction, please. Aha. Yeah. So that's good. We need to do some sacrifice first before you go for a long holiday. So anyway, to me, Deepavali, I will do some work because I've been left over something during my stay in Taiwan. Well, we don't have pretty much time. If you have more time later on, maybe after the Diwali, I can share some stories with you when I'm in Taiwan. Okay, right. So let's continue this. Let's start with this topic: fiber reinforced polymer composite. Okay. Well, this is the first generation of the fiber reinforced polymer composite. The first generation of polymer composite, I can say, first generation of polymer composite when it start invented and it becomes so popular in this subject of polymer-based composite or polymer matrix composite. So people start to actually add a different type of fibers into the polymer materials. So, and fiber actually is the initial filler, and some part of it, some of them, they are the reinforcement to be added into the polymer to become the composite. So the attractive features of these fiber reinforced polymer composite are they have a high strength to weight ratio, meaning that they are strong in the same time they are light. Okay, and then another thing is they are also quite stiff, meaning that high modulus. Then the third one is it has this one, the low specific gravity, is the meaning of low density, light in weight. No, directly, this is the directly correlation, and this we'll talk about this in a more scientific way No, if let's say for the layman people will say they are light. That's it. Okay. Fatigue strength. We'll learn a little bit about this fatigue. I think in the class, in the face-to-face class. No, I'm not going to have. Maybe we're gonna to have this online class during the festival, or we'll see how it goes. No. Anyway, after your sem break, I'm gonna to meet you another week. No. Then it will be a face-to-face. So or online. I'm not very sure yet. Okay, so then we'll talk about the fatigue. Give you a sample of exercise. Example of exercise. Good corrosion resistance. This is for sure because polymer are non-corrosive material. Okay, and when we add some inorganic material into the polymer, so the thermal expansion will be slowed down. So then it will reduce the thermal expansion. So leading to good dimensional stability. So the polymer composite material will be more stable, in more dimensional stable under a certain condition. Perhaps it depends, no? It can be, but usually elongation or expansion of the dimension will be during when it is in a hot environment, right? So in a cold environment, it will shrink, right? Mengecut. So it will shrink. That is also influence the properties of the composite. Either it expand or it shrink. Okay. And significantly anisotropy in property. Somehow, anisotropy is a same property in all directions, no? So this one is actually depends on the fiber arrangement. So students, for those, if you think that I speak too fast, and you can't catch me, please let me know. And if you really can't catch my English, and please let me know as well. Okay. If you want me to translate it in Bahasa, please let me know. Okay. Or else I will continue like this flow. Okay. Well, I mentioned about the rules of mixture, right? So in this topic, we're gonna to learn a very simple equation related to rules of mixture, and there is actually some of the students they memorize the equation, and some of the smart students they don't memorize the equation. They can actually come up with the equation with the basic theory that I'm going to share with you in these slides. No. Okay. So technically, blah blah blah. Okay. So like fiber phase, as we know, fiber divided into two types: long fiber, short fiber. Right. So of course, the small diameter of the fiber, small diameter and long in length of the fiber, usually they are stronger. And what we have learned, we call it aspect ratio, right? So the L, the length over the diameter. So they strong in the sense of they have a good strength. Well, in last week or several days ago when I was in Taiwan with you guys, and we talk about this whiskers, and okay, kids, forget about this first, okay? We not gonna to emphasize the fiber phase about whiskers, so forget about this. But anyway, in this, the whiskers will be referred to single crystal, and they are more to the ceramic type of the fiber. So just ignore this. Don't make yourself confused. I don't want to make you confused. So we just learn long fiber, short fiber. That's it. Okay. Hi. Well, what is the function of matrix? And actually, in the beginning of the class, when we learn the composite, it is very clear. So these are all the functions of the matrix. And in the quiz that I did ask, right, where the force being transferred. So in the early classes, in the physical class, when I review, and I have highlighted that the force has been transferred from matrix to fiber, right? From matrix to filler. So that is the answer for the one of the question of the quiz just now. So the function of the matrix and what are the requirements of the matrix, I guess this is quite straightforward. I will not continue it, okay? So meaning that the matrix must be ductile, so it has a good ductility. The ductility, it means that it has a good elongation, is quite kind of flexible. If compared to the fiber not necessarily must be flexible. Usually the fiber are quite rigid. So with the combination of the rigidity and flexibility or ductility of the matrix, the composite material will become a perfect product. Okay. So it has a E, lower E, meaning that is modulus. So sorry, E here is modulus. So then is something like the matrix is something react like a glue to stick the fiber together to form in a proper, make them in a proper position or proper condition, so that the fiber can stand like this, no, without spreading themselves through the things that which is not good. So they can be like this, being protected, I can say, being protected by the matrix. Here the matrix we mentioned is a polymer matrix. Okay, so I actually showed the picture before, right? When we had the physical class, I guess, and you show the fiber pull out and what is the reason of the fiber pull out, and this is a repeat. Okay, so here you'll see that influence of the fiber length. The mechanical properties depends on what? Okay, mechanical properties of the polymer matrix composite or the fiber reinforced composite in more specific, because in this topic we only learn fiber reinforced composite. So the mechanical properties of this fiber reinforced polymer composite come from the fiber itself. Okay, the mechanical of the fiber itself, and of course it is also from the interfacial addition. If you still remember, that is very important, interfacial addition between the fiber and the polymer matrix. Okay, so the load is actually transferred, okay, from the matrix to the fiber, because matrix is a domain of the composite. What I mean domain is the huge amount used in the composite material. The core domain would be the fiber. So example, 70% of the matrix and 30% of the fiber. So this 70% is become the main ingredient, and we say it is a domain. So from here, you see if the fiber is so long, okay, so and the interfacial bond that we call it the interfacial addition or interfacial bond between the fiber and matrix is quite strong, then the strength of the fiber reinforced composite is also very high. Now, you talk about this, no? We're going to have, maybe I will show you some of the some of the real question related to this critical fiber length. There is an equation to calculate the critical fiber length. So whether the composite is success or not success. So critical fiber length depends on the fiber diameter, the fiber tensile strength, and also the fiber matrix bond strength. So very simple. It is only play around all these factors only, either the strength of the fiber or fiber matrix interaction, the bonding interaction. That's all. Okay, these two, the major one. So critical fiber length, we usually put it as a LC. Okay, general applied, and can remember, since the load cannot be transferred beyond the end of the fiber, a critical fiber length likely exists for effective strengthening and stiffening of the overall part. So you will see when you pull out the stress strain curve, right? The stress strain curve will be like this, increase the stress, and then suddenly it stress out a lot and then it drop. Like it stress out very high and then it drop. So it means that actually the fiber, it has reached its a critical fiber length, which is it actually refuse to fail anyway. The load keep increasing and this fiber keep like against the force has been applied to them, and then they suddenly have a very, like we human being, if when we reach to a certain critical situation, during the normal time, we do jogging, example, right? And nobody chase us, or no animal, no what kind of this animal chasing us, and then suddenly there are critical situation happen. Oh, the tiger is chasing us in the jungle, example, chasing me, a tiger, right, going to eat me up. So I feel panic. Of course, I will use my full power, right, to run. Yeah. So something goes to the material also when they reach to a very critical situation and they try to resist what has been done to them, so they can reach up the highest power they have, and then it creates something we call the stress of this composite will dramatically increase and then suddenly it drop, something like this. Okay. Right, so actually I have a video to show critical fiber length. Anyway, let me finish this. Maybe then I found the video in the YouTube and then we can enjoy. So this is a good of an online class talking about critical fiber length. Okay, critical fiber length, the LC, depends on the fiber ultimate strength. Okay, the fiber itself, the strength of the fiber diameter. Okay, so here, this is tau. Tau is not right as a LC. Sorry, it should be pronounced as, this is a Greek word from Greek. So this is tau C. Either the tau C is here. No, sorry kids. Okay, this is tau C here now. You see my arrow, right? My cursor here. You can see, right? Huh? Yes, you can see. Okay. So this one is tau C at the bottom here. Okay. So either the matrix fiber bond strength or the matrix shear yield strength. So whichever is smaller. So whichever this is small, and then the critical fiber length will be long. So therefore, the bond between the matrix and fiber often dictates whether the fiber would improve the property. So always interaction between the fiber and matrix usually plays the major role, and as well as together with the fiber strength itself. Okay, so critical fiber length is approximately 1 millimeter for glass fiber, carbon matrix composite. Oh, this is carbon matrix. This is not polymer matrix. Okay, and the diameter of the glass fiber is about 20 to 150 millimeter. Okay, it's millimeter. Okay, so you may a little bit of so this is the equation we use. 2 over, yeah. So tau C SFD, they are the same, okay? They are the same. They are the same. So they are the same. Okay. So normally matrix has a lower modulus. Yeah, this is, we know that. And then to achieve, okay, so to achieve an effective strengthening and stiffening, okay, to the polymer composite, the fiber, okay, the fiber must be larger than a critical length. So example, this is for us to do the polymer composite design. The design, sorry kids, the design is for, I think this is for long fiber. Okay, this is only apply for long fiber. Now, short fiber, perhaps yes, but anyway, this is for long fiber. Okay, for long fiber, and the long fiber has been arranged in a proper direction. Either it is in the straight uni direction or this woven direction. Okay, so it has a well-defined directions now, the fiber. Then we use this concept of, we call it critical fiber length. So in order to know whether the composite can be produced, okay, have the strengthening and stiffening effect, the fiber length must be exceed the critical fiber length. So that is why there is a calculation on it actually. Okay. Well, from here we will see the influence of the fiber length. So this is a continuous fiber. Continuous fiber usually their fiber length is more than 15 times of the critical fiber length. So 15 LC, more than 50 times of critical fiber length. Okay, so this is a continuous. A short fiber that's why I mentioned, right? If you need a strengthening and stiffening effect of the composite, usually they are the long fiber. So the short fiber usually has a lower than the 15 critical fiber length. Okay. So for this one, you see half the share, half of the purchase. So this is a long fiber. Okay. And then this one is kind of, I can say, this is just ngam. Okay, just ngam the critical fiber length. Okay, just ngam. So the thing is just ngam here somehow is quite dangerous. The fiber length is equal to the critical fiber length. So it's kind of a little bit dangerous for us to use this kind of length to design a high strength and high stiffness of the polymer reinforced composite. So we'll usually advise to have this more than 15, and this is short for sure. There's no reinforcement will happen. Okay, so and which is lower than the critical fiber length. It's not even up to the 15 times, but lower than the LC. Okay, so we actually learned this equation. Kids, remember this equation. Critical fiber length equal to stress of the fiber. Okay, here. Okay, this is epsilon F. Is it epsilon? Maybe. Okay, this is epsilon F. This is the yield strength of the fiber, the diameter of the fiber, divided by 2 fiber matrix bond strength. So sometime when we know this equation, just remember this equation on this page. The previous page maybe will make you confused. So from this equation, we can predict what we somehow can predict the fiber matrix bond strength. Example, if we know all these 3 things, correct? So and somehow the question may ask, what would be the suitable diameter for the long fiber? For the fiber can be used to reach out this, and then it'll give you some of the information. So remember this equation. Okay, critical fiber length equal to yield stress of the fiber times the diameter. So they are all together. Okay, divided by 2 because of this equation here. So divided by 2 tau C. So tau C is the strength, the fiber matrix bond strength. So they are all in the same unit. So remember, critical fiber length would be in the unit of meter, millimeter, or centimeter. So you have to know that, huh? Okay. I will find a video later while you have a short break of 5 minutes. Okay. Well, First one, this is the influence of the fiber length. So from the influence of fiber length, we learn about critical fiber length, okay? And this is the equation, okay? Then the second factors is the fiber orientation. I think I mentioned this in our physical class as well, okay? We'll see this is the unidirection, okay? And this is the longer fiber, short fiber, a shorter one, but still can consider. And in one direction, and this is the transverse, this is very short and it orient in a, like, I don't know how to say, but anyway, okay. Right. So I have a question here. Okay, before we move. Example, this is one directional fiber reinforcement, okay? The fiber go to the same direction like this, right? If something like the force is pulling from this side, you see this is arrow, okay? The force pulling same direction to this fiber arrangement. So, and another force, example, this is force A, same direction. Force B is the opposite direction of the fiber arrangement. Okay, so which will give a stronger stress? Okay, same direction to the fiber arrangement, or A or B, opposite direction to the fiber arrangement, which will give higher strength at the different applied force direction. So A or B is stronger. So let's vote now. A or B. This is a long fiber, continuous long fiber polymer reinforcement. Same direction A or B, different direction. Then you will get a higher strength result. Which one? Hello. Can I have your attention? Can you please vote? You have only two choices, either A or B. A stronger or B stronger in terms of strength. Hello, please don't waste time. We'll finish this by in 1 hour. Okay, let's vote more. Let's vote more. No, vote more, but more students to vote. I need more students to vote. Okay, good. Got some. How many already? B, 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 B. More? 2 to 3 more. Which one will give highest strength? Same direction or different direction? Can I have 2 more? Okay, so all answer B, correct? All B. How about Sean, Chai Mei didn't vote. Chai Mei always very active, right? Chai Mei didn't vote. How about Arif, you vote or not? Or Chai Mei vote already? Okay. Okay, so Alif, you want to vote? I didn't see Alif leh. Alif, how come? Oh, Alif, how come this day you are quite quiet? You are very tired or what? Usually you are very active in the class. Oh, Alif vote also. Okay, sorry. I'm getting, I find Alif in. Okay, good. Okay, so thank you. Thank you for voting. Okay, I kind of quite enjoy with you guys actually. I love your batch actually. Love your batch. Okay, so well, the answer is A. The answer is A, not B. Okay, the answer is A. The answer is A. Perhaps your thinking is, oh, because the direction of the I think you may think that because if the load apply to the opposite direction to the long fiber, so the long fiber will start to fight, correct? Right. That's why you choose B. Right. Actually, the transverse direction, the fiber length will reduce. In the same direction, the fiber length is even longer. So actually, just remember when the same direction of the fiber is very, very long. So when you pull it, you need actually higher energy to, higher energy to break it. So, but the fiber is like straight, very long, go straight like, but you pull in this way, this is only the diameter. So diameter is shorter, right? So then the energy to break it is kind of very easy. So the transverse direction have a lower strength compared to the longitudinal. So we call it, this is stronger, this is weaker. So your answer is the ballet. Never mind, you give the wrong answer, then you remember, correct or not? Okay, so you remember this? Like, okay, good. So this one is okay. The fiber orientation. So let's see, stage 1, 2, 3. Well, this is not very clear for this failure none. Okay, let me check about this along the fiber. Yeah. Okay. So in short, just now I have been like I have been explained to you. This is actually related to the critical fiber length again now. So this I have been mentioned just now. If the force is to the same direction of this long fiber, so it need more energy to break them. So because they have this high critical fiber length, no. So another one, if it is opposite side, then the energy required is kind of a little bit lower. So this is the thing. Okay, so this is the what we call 20 LC, the optimum. Okay, well, this is 30 times of the fiber length, so that you can like calculate whichever that we would like to have. So thinner fiber will help too, and diameter decrease, the critical length will be increased. Well, okay, so I pass through this. So the answer is same direction, okay? So properties of and it is related to the critical fiber length. Again, just now I mentioned the length, okay? When fibers are aligned, one direction, we call it one direction. So the material are highly anisotropy, meaning that anisotropy is 1. So the property of the fiber reinforced composite very dependent on one direction only. So if example the application applied to that direction, then that direction will give the same direction will give the best, but opposite direction will have a lower property. So it is kind of, we call it a very it's a directional dependent, I can say that. So if let's say we have a short fiber, okay, and the short fiber, it arranged them randomly without either in the straight way of align themselves, or in the vertical or horizontal way, or like this cause, I don't know how to say it, cause the woven direction or whatever, then the properties of the composite will not be influenced by the fiber arrangement because they are randomly arranged themselves. So okay, modulus perpendicular to directional lines. Okay, so here we talk about the strength modulus, no, and it is same goes to the modulus, no, it is the same go to the modulus. So modulus in direction of alignment function of the volume fraction of fiber and modulus perpendicular to direction of alignment is considerably less. Perpendicular is opposite direction. So it will be reduced the modulus as well. Okay. Randomly, just now I mentioned randomly of the randomly oriented fibers, the properties are not dependent. The properties are independent to the direction. So whatever we pull here, pull there, the strength should be the same. Actually, the strength should be the same. But anyway, in the reality, it is not the case. In the reality, it is not the case. Somehow it will be a little bit lower than the strength or higher a little bit. Well, this is the reality. So nothing is perfect. Okay. Okay. So we come to this now, kids. We come to how to derive the equation. Okay. This is important. Okay. How to derive the rules of mixture. Okay, so we move the important, and the rules of mixture is only applied to fiber reinforced composite. It is not applied to others type of short fiber. No, this is only applied to short fiber, long fiber. Okay, so just be very specific on that. So we come to how we going to derive the equation. And then we can predict the properties of the fiber reinforced composite, the long fiber, not short fiber. Okay. We consider, but we have some rules to consider. We can't actually say as you learn mathematics, you are very good in mathematics. So all engineers should be very good in mathematics, right? But somehow I find out I'm getting lousier in mathematics anyway. So when we want to apply a mathematical model, we need to obey some regulation, correct? So these are the regulations that we just assume. We just make an assumption. You see, the basic assumption in this vastly simplified approach are as follows. So we need to do some assumptions. So without assumptions, it is kind of difficult. It's kind of difficult to come out with a mathematical model. Okay, so now is for us to predict the modulus of the fiber reinforced composite materials, okay, in a different direction. So we just need to learn two directions. One is the perpendicular direction, transverse or longitudinal direction, or transverse direction, only two. We don't learn more, okay? For during my time, we learn more. My professors teach us a lot, but okay, anyway. So now, we have to make some assumptions. So first, we have to assume that the fibers, the long fibers, are uniformly aligned very well in the polymer matrix. That's one, first assumption. Second assumption is the polymer matrix, the fiber and the matrix, they have a good addition. So meaning that the fiber are perfectly wetting by the matrix. So all the fiber, all surfaces or the fibers has been protected or wet, or glued by the polymer. Okay, we have to do this type of assumption. Okay, the third assumption is there is no void or no failure, meaning that tak ada bubble, tak ada air bubble, tak ada tempat kosong-kosong, okay, no void in the composite, meaning that it is kind of perfect. So, okay, that is the third assumption. I may ask something question like this. What before you do the prediction of this mathematical model, okay, of this rule of mixture, we are going to enter the rules of mixture. What will be the assumptions that we have to follow? What are the assumptions? Please determine several assumptions before you derive the equation. So these are the 6. Maybe I just need to ask you to answer 3 assumptions. You don't have to write all, maybe part of them, half of them. Okay. Assumption number 4 is, so assumption number 4 is the force applied parallel or perpendicular to the fiber direction. Okay. Then if it is a laminar structure, that you're going to learn from Dr. Aslin, okay, laminar structure or layered structure, so the initial stress is free. So no initial stress will occur in this kind of layered or laminar structure. Anyway, there's always happen that is, but this is kind of in a perfect situation. Okay. The last one, both fibers and matrix behave as linearly elastic materials. So linearly elastic materials meaning that they follow the Hooke's law. You remember the Hooke's law? Meaning that they are flexible, right? Okay, only Chai Mei. How about the others? I didn't get some answers from the Indian students now. Because I always like, you see this like, got the few of the Indian kids I was there, and then the Malay boy, Malay girl, yeah, okay, pretty good. Okay, good, we have, okay. So I try to let everybody active in with me. So not only always listen to like Chai Mei, Alif, Jeff, of course Kurt, and then sometimes Sean. Yeah, I try to help Sean. I know something not really good happened to Sean, but things can be improved from time to time, Sean. A mistake is not a forever mistake. I just want to tell you. You know what I mean?
Doctor.
Yeah, okay.
Yeah.
I want to encourage you. Okay, so you have done the mistake before, I know, but it's not forever. Okay, so learn from the mistake, move forward to be a better boy. This is what my advice to you. Okay, Sean. So hopefully
Alright,
you did
Doctor.
well in my class. Okay, I would like to help you. Okay, don't do the mistake again. Okay, right. So both fibers and matrix behave. So this is like a perfect assumption. No, kids, you have 6 assumptions here. So perhaps in the exam or test, I will just ask you to give 3 assumptions, right? So before you come out with these derivation steps now. Okay, elastic meaning that the fibers and the polymer will be flexible, and they are like a rubber. They obey the Hooke's law. Anyway, basically to me, this is kind of but fibers usually it is not obey to the Hooke's law. For the fiber types, it's not obey to the Hooke's law. So somehow it's quite difficult. But anyway, but if you want to put the rules of nature to derive a good equation, and not a good equation, but to derive to come up with an equation that to help us to do the prediction. Okay, this is just a prediction, kids. Prediction doesn't mean that it's accurate, correct? So it just we can do a prediction to help us to design a better composite material. This is what I can say. Okay. So now we come to the first one. Let's, this is a rules on mixture. The first one is we would like, for the case A, we would like to predict the modulus of the composite, polymer reinforced composite, which the force, this is long fiber, okay, which the force applied to the same direction of this fiber arrangement. We call it longitudinal, okay, or perpendicular, or same direction. I can use different kind of word to say, okay. So now, consider composite model containing certain fiber volume fraction. We use volume fraction, we don't use weight percent, but after the volume percent, we can change it to weight percent. But here we focus on the volume percent. So volume percent of fiber, okay, volume, volume, like density equal to volume divided by weight. So this is volume. So the volume of fiber, but it's volume fraction, meaning that it's unitless. So it is formed from uniaxial aligned continuous fiber. And so see figure 1 and figure 2 here. Okay, so this is a cross-sectional look of the composite. You see dot here. Actually, if you cut it like this, you see like a dot on it, no? But they align very well, no? And this one is the a direct, yeah. So you cut another way around, you see like this. So the matrix is blue color, the fiber is black color. Okay. Now, come to the next slide. Okay, when the force is applied continuously or the same direction to the fiber arrangement, so meaning that the elongation of the fiber is consistent. Okay, elongation of the fiber is consistent. So meaning that we call it isostrain. So the elongation of the matrix equal to elongation of a fiber and also equal to elongation of composite. Composite is the general, and not general, it's a combination of the matrix and fiber, right? So we call it, in this condition, the strain, the fiber strain is consistent. There's no change. They elongate in a very systematic way, the length. Okay, so we can put something like that. We call it isostrain. So EM equal to EF equal to EC. They're all the same, regardless of composite, fiber, and matrix. Okay. They elongate the same strain. So we call it isostrain. Okay, they're right. So then the force, of course, the force of the composite must be equal to the force come from the matrix and the force come from the fiber. So F is equal to Fm plus Ff. Okay, then we resubstitute the force. Okay, the force now change to, right, the stress and the area. Okay, so we rearranging the force. The force of the is equal to the area times the stress. Okay, area times stress of composite is equal to force, right? So you put it like this. Then after that, we just need the stress. Okay, the stress of the composite. So left, the stress of the composite is equal to Sm per Sc divided by Sc divided by Sc. So this is a pretty easy mathematic, right? The area of composite divided by area of composite divided by area of composite. Okay, so you derive this. Okay, you derive this where this is area of matrix divided by area of composite, and area of fiber divided by area of composite. So they become, this is actually the volume fraction of fiber, and this is volume fraction of matrix. So here I have been explaining it quite well in this slide. Okay, so the area of fiber divided by area of composite is the volume fraction of the fiber. Okay, so because they have the same, how can I say, they have like a same if fiber, they have a same length. Okay. Okay. If the fiber length are all equal, so they have the same length, and if they have the same length, they have the same width, I can say. Okay. So we can turn this area of fiber divided by area of composite is actually is the volume fraction of fiber and volume fraction of the matrix. Then we can, how to say, we can replace this as C, right? And then equal to the stress of the composite equal to the stress of the matrix times volume fraction of the matrix. Okay, if you go back to this volume fraction of matrix, and then this volume fraction of fiber. Okay, we simplify this. So SF, VF, sorry, this should be VF. Okay, kurang satu F kat sini. Okay, VF. So then we actually can predict already the stress. Only the stress. It can be yield stress. We can predict the yield stress. Okay. Okay. Or we can predict the this can be yield stress. This can be tensile strength. Yeah. Okay. Or this can be fractional strength. Long fiber, same direction. Anyway, it's just tensile. Okay. Just tensile. Not fractional. So each shot, this we can predict the strength of the composite or the yield strength of the composite equal to the strength of the matrix itself times the volume fraction of the matrix plus the strength of the fiber itself and the volume fraction of the fiber itself. So this is a pretty straightforward equation. So in another way round, okay, in another way round, the strength is equal to strength times the modulus, right? So we substitute this little EE inside, okay, little EE inside, okay, substitute this SC, SM, and SF. Then we actually can predict the modulus of the composite is equal to the modulus of the matrix times the volume fraction of the matrix plus the modulus of fiber times the volume fraction of the fiber. So this is when it obeys the Hooke's law. When it obeys the Hooke's law, then we can do something like this. So we can predict the modulus of the composite. So in the same, when the force applied to the same direction of the fiber arrangement, then it is an isostrength. So from there, you can slowly derive the equation. It's not long derivation. These are all semua ada markah. So then you come to this equation. And for this, we not only can predict, okay, for information, I only stop here, right? We not only can predict the modulus of the composite, we also can predict the yield strength, the tensile strength, and also the density of the composite. We can predict 4 things in this equation. We call it rule of mixture. Clear? So we can predict 4 things, okay, using these rules of mixture for the same direction. When the force applied to the same direction of the fiber arrangement. Okay, so kids, you clear? Make a note for yourself. So please give some reaction if you are clear. If you're not clear, you can voice up. Are you clear? I need to see your reaction. Okay. Who else? Okay, Jeff say okay. Then the others? Okay, Shara. Okay. Right. How about the Malay boy and girls? Okay. Right. Okay. So remember this, although I didn't mention in the slide very clear now. So you can predict 4 things in this equation. You just change it, no? Example, if density, okay? Density of the composite is equal to density of matrix volume fraction of matrix times density of the fiber times the volume fraction of fiber. Just change the E to density, to strength, to yield strength, then they are the same. So you can do the prediction. It's for predict, no? Okay, these are the same. I'm not going to talk about, let me check, what is this, kids? No, this is the perfect bonding. This is iso strength. Okay. Ignore this slide. Okay, I'm sorry. They are kind of okay. Okay, now I'm gonna to tell you another one. It's actually, we call it it's not isostrength, but isostress, but perpendicular. Let me check. We have so not yet now. So kids, I think I have to delete this slide. It make you very confused. I tried this. Ignore. This is quite of confused. Just remember the before one. I find it is simple. This one is make you confused. Okay. So this is an example of question. Okay, this question is very straightforward. Okay, you can practice by yourself. Okay, so example, very easy question. You see, composite, the fiber reinforced polymer composite modulus for polyester. This is a polyester together with glass fiber. So some of the information has been given. Example, this is modulus of polyester, modulus of glass fiber, and then the volume percent. So sorry, polyester reinforced with 60 volume percent of E-glass, meaning that 60% glass fiber volume percent. This is in volume. So very straightforward question. 40% of glass fiber, 60% of glass fiber, 40% of polyester. So the volume fraction. Okay, now my question is, what is the volume fraction of glass fiber here? So volume fraction is no unit, right? So unitless. So it's equal to how many volume percent here? If let's say the glass fiber is 60%, 60 volume percent, so the polyester is 40. Total is 100. This is very straightforward because only two materials, no? So what is the volume fraction of glass fiber here? Here tell you 60 volume percent. So volume fraction will be equal to, can anyone tell me? Then if you know all these, then you just pop in the digits inside the equation of just now you learn, then you get the answer already. So what is the volume fraction of glass fiber? My question. Can you get some idea? What is the volume percent of the glass fiber, volume fraction of the glass fiber? Fraction usually plus A plus B equal to 1 only. Yeah? It's called fraction. Right. Okay, so I have to tell you this. Okay, so the answer is 0.6, no? So the volume fraction of glass fiber is 0.6. Okay, how come 2.5? Jeff, you make the world so difficult, ne? 2.5, 2 over 5 equal to 0.6 ka? Alamak, 2 divided by 5. No, 0.4 only. Okay, so I asked the volume fraction of glass fiber is 0.6. Okay, so the volume fraction of polymer of the polyester is how many? So we know the volume fraction of glass fiber is 0.6 now. So how about the volume fraction of? Yes, okay. Okay, so 0.4. or 2 over 5. Okay, anyway, as long as your answer is correct and how you do it, I don't really care. Okay, so then you know, you just put it in, right? You just put this polyester 6.09 10 to the power 3 times 0.4. Okay, polyester is only 0.4 plus 70.2, okay, times 0.6. And then the answer is that, straightforward. So this is a kind of very easy question because the answer is under isostrain condition. So what you just learned, under isostrain condition. Okay, so clear? Just one example. Now we move to the second equation, also the last equation. Okay, I'd like you to derive this. No, this is a little bit of difficult, but anyway, it is doable. How about we now would like to calculate the modulus, which is opposite to the force applied opposite to the fiber alignment. So we call it transverse or perpendicular. Okay, so like this. This is the fiber arrangement. The force is opposite to it. Okay. Then in what condition? There will be something similar as well. In what condition? So just now we learned is an isostrain. So the elongation is the same. But now when it happened to this opposite side, then we can say it is an isostress condition. So each layer is perpendicular to the direction of loading and has the same area of the load because its count is area. It is no longer the length considered. Okay, so then each layer carry the same load, experience the equal stress. So they have the same stress, meaning that the stress of the fiber equal to the stress of the matrix and equal to the stress of the composite. So come to start with this. Same stress. Okay. So from here, we have the strain. So we have to replace, okay, we have to replace the stress into the strain. Okay. So the total strength of the composite is given by, this is composite, no? Okay. This has been simplified. Okay, guys, it has been simplified. I think I don't have another. Well, I don't want to make you confused. Then I give you a quiz, right? But that is not a quiz. It's just for you to do. Okay, so it has been simplified. The stress, you know, the stress per area is the same things. We need the area just now that you learned previously. You apply it. Okay, so then you got this. The strength of the composite is equal to the strength of the matrix times the volume fraction of a matrix, and is also equal to strength of the, so you change the stress to the strength and the area. You understand, right? Okay, just refresh just now what you learned, but I simplified one step ahead already, so it become a simplified version. Supposingly here is the A something, okay, then it convert to the volume fraction. Okay, so it become like this. Is still the stress, no? So change to the strain. Okay, now still we gonna to do the Hooke's law. Okay, gonna to obey the Hooke's law. So we change this strain, go back to the stress in general divided by the modulus of the composite. Okay, and then same apply to this, apply to this. Okay, then we actually have to delete this stress in general one, the main. Okay, then in short, when after we do the derivation, we get this. This is much difficult equation. Correct. So this is the transverse equation. And this equation only, it only can be used to predict the modulus. Usually the question will be only ask you to predict the modulus, no other information. Just now, the iso strain, you can get a lot of information, correct? I told you 4. But for iso stress, only get 1 information. You can only predict the modulus, no others. Okay, so somehow you have to be very careful of this. At the bottom, modulus of fiber times volume fraction of matrix, no? Because some of the students, they do not know how to derive this. You can make it in more detailed derivation steps, no? I have been simplified it because the previous one I give you quite detailed. So then you will get this EF VM plus EM VF. Remember this, there are huge difference. Okay? Okay, right, okay. So, okay, Sean, okay. So now, let's talk about this. Okay, this is somehow, so we learn about these two, the rules of mixture from these 2 equations. And I have to repeat, these 2 equations are useful for long fiber reinforcement. Now, not for short fiber, okay? For long fiber reinforcement. And we can get actually more information. Okay, we can get more information from the longitudinal loading rather than the transverse loading. And these 2 equations are fall into the rule of mixtures. This is a traditional polymer composite design equation. Anyway, I find out there are not much people use this anymore because due to the advancements of polymer composite, people no longer, the fiber reinforced composite has been so matured. I can say the technology of it is quite matured right now. And this become makan kacang already in the industry. And this is the basic that we usually teach the students. At least they have this mindset. Oh, initially the history of our subject is come from like this, no? Okay. But in the publication wise, in research wise, we seldom use it anymore. Why? Because there are so many types of advanced polymer composites appear in the world right now. So they are no longer use the fiber, something like those traditional fibers like you learn right now. Carbon fiber is still very popular. Okay, glass fiber, whatever, because they are all quite mature technology. So the advanced version is people use a smaller fillers, smaller size of filler, and two-dimensional type of fillers. So these rules of mixture cannot be applied anymore. So that's why you don't really read a lot of this in some of the published work anymore recently or 10 years back. Okay. So remember, these 2 are important. Okay, these 2 are important. How to derive them? Okay, and then answer some of the questions. I will share some questions to you when we meet. When we meet in the class next week. Okay. So here is like something a summary of these 2. Then for this type of longitudinal loading for long fiber, it is stiff and strong. If the load applied same direction. Just now I have told you. Then you need to do some calculation, then you will know. And this is kind of soft and weak. Okay, right. So now, we have something like a lower boundary. We have these like a 3D graph. This is the modulus of matrix, modulus of fiber, and concentration of fiber, or we can say volume percent of the fiber. Okay. Interesting part is that somehow I raised some questions to the students before. Well, this is for us to think of. Is nothing right or nothing wrong, or not 100% wrong or not 100% right. Okay. In the calculation, we use volume percent, correct? You see the volume percent, the volume fraction. Yeah. But in the reality, when in the market, they're selling the product, they use weight. Many of them actually are using the weight. Correct. Using the weight to sell the product, the weight of the fiber, the weight of the polymer. So in another way that we have to do the calculation, convert the weight to volume, then you can only apply this equation. So something it is not straightforward that I can say in the practical world. Something is not straightforward. So, well, I cannot say it is wrong. I cannot say it is totally right or it is totally wrong. Okay, so this is the trend, the market while doing now in the real world. So here we have the example like this, and in order to design, okay, for the composite design, for the long fiber composite design, the engineer will plot two, like this 3-dimensional, like it has a two y axis, no? One is for the matrix, one is for the fiber, and this is the weight of fiber or concentration of fiber or volume percent of fiber, whatever. Okay? Then they will have to make sure that the modulus that they obtain from this different concentration of fiber, they are fall within this range, meaning that it have to be within the isostrain, and it cannot be lower than the isostress. You get what I mean? So isostrain usually it give you a higher result, right? So higher result. And then the isostress, the perpendicular usually give a lower result. Yeah, lower modulus, this higher modulus. So the industry will make sure that the product of this modulus that they obtain is within this range. Yeah, it cannot be sometime it above here or it below here. If you work in the industry before, like industrial training, I still remember some of the questions did pop up to me is when we design, we have a certain upper limit and lower limit, we call it. This is called upper bound and lower bound. So the industry has its guideline to have this upper bound and lower bound of the result after we do the test. So it must be fall within this upper and lower. If there's 1 point beyond this and 1 point beyond this, we cannot accept it. Have you gone through this during your industrial training? Yes or no? They will set an upper bound and no, right? I think recently, the students go for training, they don't really learn very good things. I don't know what happened. Well, during my time, we learned a lot of things. Like the company will teach you, okay, this, and then we have this limit. You get the 10 weeks. Okay, my time, I also did my industrial training 12 weeks, about 12 weeks. Same like you, I come from a technological background, but I'm not sure. Maybe it depends on where you belong. So I learned quite a lot from there. They'll give me a table like this. Now this will be the result. Then the test result must be fall within, I call it within the upper and lower bound, something like this. This is quite common practice in most of the industries. Okay, fine then. Right. So here is a repeat kind of thing. Haha, I have this is quiz, no? I'm not sure whether I want to give you the quiz or not. Anyway, maybe we do it when we meet. Okay, we do it when we meet. Okay? So we will do it when we meet. Okay, for this question, I will keep later. Okay, we do it when we meet on Tuesday morning. All right, is it okay? Okay, or I may find something else. Yeah. Okay, so let me. Okay, I have 10 minutes, so I want to be with you for another new topic. Okay, and I will share the notes later after the class. Is it fine? Okay, so like I have only 10 minutes, so we do something little bit. So here I make a in what we learned in the past 1 hour is about derive of the rules of nature. Okay, and then I emphasize what are the for us to do the composite prediction. Okay, now we go to lecture 5. 2, 4. Okay, we talk about the mechanical properties a little bit. If you have done it, then okay, wait. Right. Okay. Talk about these mechanical properties and hardness of polymer matrix composite. Okay. So I believe you have learned this quite well. These are all about the short performance test. We call it short performance test. No, the tensile, the flexural, the impact. No, they are all the short performance tests. Correct. So meaning that you will get the result immediately, just maybe few seconds to few minutes, upon the failure of the material, upon the failure of composite material. Then you're gonna you will get the result immediately. After a few seconds or few minutes, and the composite will be all destroyed. So the material must be destroyed. Okay, the material must be break into two, or must be broke. Or must be broke. Then you only can get the result. But anyway, somehow some interesting part happened to us, right? You remember when we were in the classroom? I remember during your second year, we go to the lab. You remember or not? Then we do the flexural test. The material is not break. Do you still remember when you were with me and with Dr. Nasri about the subject in your second year, structure and polymer structure and applications. You remember that? Then we go to the lab. Then we do tensile, flexural, impact, hardness. We do 4 tests. I still remember. And then something bad happened to me with the technician. And then you guys will feel, how come he's so rude to me? You remember that? Shan't forget. I think it happens to some of the kids only when Chai Mei was there. Yes, because you guys were divided into several groups. So we didn't meet every week. We meet rotating like this. Like I remember Chai Mei was there, and also Abang, and hopefully I can see him back here. So yeah, so we did, and then the fractional test was not being break. Then we still we still use that result. You remember that? Supposedly it should be break, no? Okay. Well, so the result of this, we call it short performance test. Short performance test meaning that you can get the result in a short period of time, example, in a few seconds to few minutes only. So that we call short performance test. And these tests that you have been performed, they are the destructive test. Okay, you're going to learn non-destructive tests later. So they're called destructive test. Okay, so the destructive test is your material will break. Okay. Now we talk about this. I'm not going to repeat of the impact or whatever because you have been learned. Now we need to talk about these three things: fracture toughness, fatigue, and creep. Okay, these and especially fatigue and creep, they are belong to the long performance test, meaning that it will get the result in a few weeks or months or year. Only will get the result. Okay, so it's kind of very slow motion of the test that it will perform to the polymer composite material, and it is very commonly used to a metal material. Yeah, these two are very commonly used to metal material. Okay, these two are long performance. Fracture toughness is not. Fracture toughness is short performance. Fracture toughness is actually to know, to measure and to determine how good is the material can resist to the, how can I say, to resist to the failure when there is a crack happen on the composite. Meaning that we create a failure point already. There is a failure point created on the polymer composite, and then we measure, we do the test. Then the test we still can perform using the tensile test. So in a real situation, nothing is perfect, correct? So when polymer material, when the composite material has been used for a certain period of time, then there will be a little crack maybe has created, little crack has been occur on the composite, and then that is the initial failure will start to the composite, right? So then the scientists were still interested on it. So they would like to determine still how good is this material can stand the force without before it break. Although there is a presence of cracks, then we call it fracture toughness. Have you learned this from Dr. Dare? Because your junior, your senior told me they have learned this from Dr. Dare. How about you? Or the learning things becomes lesser and lesser? I'm not very sure. Have you learned this from Dr. Tay? Have you heard this fracture toughness? Hello? Have you heard about this fracture toughness? No idea. Oh, since Taimei cannot remember, meaning that there's no. Okay, never mind. So, yeah. But so Sean heard or no? Because Taimei say no idea, and then Sean thumbs up, and then and then I should call Kurt. Kurt say yes, doctor. What is the mean by yes? Yes is you never learn. You never heard about this fracture toughness. Like what is that yes mean, Kurt? Or how can I call you? You are Kitana. So Kitana. So how got learn from see Kita say yes or China no idea. My God, macam mana ni budak? Or FYP. Time is not focused. Interesting. Okay. So I think Kitana is because she learned FIB. She is a Dr. Tess FIB student, so she learned this fracture toughness from her. Yeah. Okay. Then in the class, you guys not yet learn. Okay. In the class, you guys not yet learn. Okay. So pretty clear is this. In the class, you'll not yet learn. Okay. Aside from those do the FIB project with Dr. Teh, I can say so. Okay. Yeah. So we okay. So we stop here. Okay. So in this topic, I'm gonna to only focus on the three things. No, later on, fracture toughness, fatigue, and creep. Okay. So because the rest you are quite you know quite well, so I'm not going to repeat. And some of the slides here is for your revision. So is it okay? Yeah. So Tuesday I'll see you again. Then we have another quiz, and then we do some exercise. Then we can dismiss. And maybe I project one video about critical fiber length. Okay. Right. So okay. So I was have another yes. We have another quiz on Tuesday. You are right, Jeff. You have another quiz on Tuesday. Okay. Yeah. So see you next Tuesday. And bye bye everyone. And happy to see you again and looking forward to meet you personally on Tuesday morning. Bye. Okay. And happy Sunday. Enjoy the rest of the Sunday. And maybe I would like to on the Tuesday I would like to learn some of from the Indian students how you celebrate the Diwali because in Taiwan the Diwali celebration is quite huge in the campus because they have a strong association, Indian association in Taiwan. There are about thousands of Indian students study in Taiwan. I think about 10,000 students. About 10,000 students, Indian students study in Taiwan. So they have a very strong Indian society in the whole Taiwan. And then they usually have this big Diwali celebration. And I somehow got a chance to attend once, I guess. And yeah, so I'm not sure. So the Malaysia here, maybe you just celebrate by yourself, right? Among yourself, not like because the Indian in Taiwan is kind of a huge group of them. They have a very fantastic festival, and it's a lot of them to gather together, and they bring a lot of foreign students as well to join them. And last time I joined them, I wear the sari. I kind of borrow from the friends. It's kind of fun with them, especially abroad. They really okay. So well, I'll see you on Tuesday, and bye bye. Okay. Okay. Bye.